So while you copy these down, I'm going to get a piece of graph paper pulled onto my digital screen here, but you can copy these down. So this I have marked as example number 1. So we're going to graph this. X plus 2y is no more than 16. X minus 4y is no more than 4. And then we're going to have 4 simple constraints. And I will say that a lot of real world, guys, don't touch each other with your rulers, please. This is exactly what I'm talking about. Thank you for stopping. A lot of problems in the real world deal with just one simple idea, and it's just a statement that something can't be negative. So like whenever you see a constraint like this one that I just circled, all it's saying is this is a non-negative value, right? So you'll see these simpler, like single variable vertical horizontal constraints. You'll see them very commonly. And there is one more. I started yip-yapping and got sidetracked, but there is a 6th constraint here. So the idea is that we're going to graph them all on a grid. And just like we've learned, we're going to see where they come together. Where the shadings agree or coincide is what we call the feasible region. And I'll spell that out for you when we actually get a feasible region on the board. So let's get to it one by one. The first 2 are going to be a bit of a drag. It's normal though. You got to manipulate equations to make them look the way you want. So if we were going to take this top one and prep it, what would we do first? So you guys are, yeah, this is just basic algebra 101, right? Get that x on the other side. So call it now negative x, right? It's like our battle cry from like 8th grade, 9th grade on is get y by itself. We need like flashing posters that say get y by itself. And then what do?
Divide by 2.
We divide by 2. Should we switch our inequality sign?
No.
No, we should not. And so we're going to have a final graphable answer of y is less than or equal to negative 1/2 of x plus 8. Okay. So I'm going to take this original top one out, and in its stead, I'm going to replace it with the graphable version. Right. After this, we'll only have a little bit more work to do because those bottom 4 constraints, those are easy, right? And again, you will see a lot of those. So that's the good news. It seems like every problem is going to have like 2 or 3 kind of more annoying ones, and then quite a handful usually of the simple ones that just block us from things that don't make sense. So for the second one, I'm assuming you would move the x to the other side. So you'd have like negative 4y is less than or equal to negative x plus 4. And then we would divide by negative 4. Should we switch the sign? We should. Good. So we're going to get y is greater than or equal to, what's our slope? 1/4 of x, and then our y-intercept is -1. Good. I've been telling my other classes, it just happens right now that you guys in Algebra 1 are doing a lot of the same stuff like skill-based wise. The work you're going to embark on Monday is significantly more difficult, but both my classes right now, Algebra 1, Algebra 2, are really getting kind of caught up in this graphing inequality stuff. So it's made for some interesting days for me, the fact that everybody's like doing the same stuff. So get this in here. And that'll be the end of the actual work that we have to do because now all 6 constraints are ready for us to graph. So this is where you and your pencil and your ruler and your knowledge about solid lines, dotted lines, which way to shade, this all comes into play. And one other thing before you make this observation, this is not accidental. A lot of real world constraints have the or equal to, because we tend not to say, like if we were writing a model for like, how many hours should Marcus work at the daycare and then how many hours should he work at his Dairy Queen job? Generally, employers are going to say you just can't go over 40 hours. And that kind of language implies that you can go to 40, you just can't go past it. So you'll see a lot of or equal tos. In fact, I think every problem in today's notes is an or equal to. So we don't have to stress over dotted lines for a while. Keep an eye out for them, but just know they're probably not going to show up for a bit. So for this top one, where are we going to start our graph at? Positive 8, so up 8. 1, 2, 3, 4, 5, 6, 7, 8. And what's the slope?
Down 1, right 2.
Nice. So I'm going to go down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2. And then I'm going to make a line like this. All right. Just remember to stick arrowheads on it, even though it feels it's kind of somewhat of a formality. It's still just what we've always done. It's what we always will do. How about the next line?
Down one.
Down one. So I'm going to go down one, and then the slope is,
Up one, right four.
yeah. So up one, right, 1, 2, 3, 4, up one, 1, 2, 3, 4, up one, 1, 2, 3, probably right about there. Something like that. Yeah. Sorry, I got a little lazy with my first line, so I wanted to fix that. It doesn't look wonderful, but it'll do. Let's take a quick moment and talk about some shading before it gets away from us. The first line that we graphed, where would the shading go relative to that?
Down.
Yeah, good job. So if this were just a single inequality, we would shade below that line because that's what it means to be less than a line is to be below it. And what about the second line? It'll be above. So at this point in time, we've got the infamous triangular sort of, it kind of looks like an alligator's mouth there, but we've got the infamous triangular region with the corner and then this big infinitely expanding cone of shading. But this is where now the multiple inequalities come into play. So we're going to start. Have you ever seen like the original Star Wars, or I think it was in the original where they get stuck in the trash compactor? You know that scene? And so that's kind of how inequalities constraints work is they come in and they start just walls just like crushing and closing inwards. And so we have another one now. This fellow, I just circled him in purple. What is he?
It's horizontal.
He's a horizontal line. That's always the answer that I'm looking for. Very good. And so because it's horizontal, it's essentially just going to be a recopy of the x-axis. I'm going to go to where y equals 0. I'm going to graph a horizontal line like this. And where will the shading go relative to that? Good. So the pieces are starting to come together, and we start to see now that the region is beginning to form itself. I hope you understand something that this area that I'm marking in yellow, it just got taken out, right? It's no longer valid because I guess it never was valid, but don't think that that's part of your solution because it's below the red. So um, let's go down to this green one. What is this?
Right, they're a vertical line.
So I'm going to go to vertical. I'm going to go to where x equals 2, and I'm going to graph a vertical boundary down from here. And which way will the shading go from there?
To the right.
To the right is correct. Good. That's the right answer. My bad. Everyone's too tired for my stupid jokes. Apologies. So you see the region starting to form yet?
Mm-hmm.
Okay, all those lines are working together. It currently has 4 walls. It's got the green vertical wall. It's got this little baby purple wall down on the bottom. It's got this super almost flat red bottom, and then it's got this slopey roof red top over here. But there are 2 more constraints yet to come in. And every time you add a constraint, it's just more area that's not valid anymore. If you leave the feasible region, now you're breaking at least one rule if you're not in the inner polygon. So for this one, so this is another vertical boundary. Everybody agree? Okay, so we're going to go to 8. So we're going to go to 1, 2, 3, 4, 5, 6, 7, 8, and we're going to graph a vertical boundary down here like this. And where will the shading go relative to that boundary? To the left. Very good. I'm going to pause my recording for a minute so I can get these people what they need. So hold on a sec. Right. Pausing is over. And finally, and I'm going to make this look a little bit brighter here in a second. We do have one more constraint, and I'll make this one, I guess, red again. And what kind of line is that?
Horizontal.
Horizontal. So we're just going to go up to 5. We're going to go up 1, 2, 3, 4, 5, and we're going to graph a horizontal boundary, and the shading will go down. So this is a good time for me, since I have the technology and I can do it, to zoom in. And it's hard with all these colors, but eventually what we figure out is that there is a very well-defined region in the corners of it. I'm going to highlight them for you. I'm going to put some white on them. There's a corner right there in white. You can see that there's a hard, another 90-degree corner right here. There's a very soft, breaky corner right there. There's this yellow-red corner right here. There's another corner right here. And then there's another soft corner up here. So I hope you're able to make sense of that, that when all the walls press together and all of the rules are followed and all the constraints are met, if you're anywhere inside of this region, then you are in, I'm going to spell this out as soon as I'm done coloring, what we call the feasible region. And whatever constraints there might be, I hope you find the next section interesting. It's very nice applicable mathematics. And if you're anywhere in that white shaded area, then you are a solution to the system. And so again, that white area has a name and it is called the feasible. What does it mean in English when we use the word feasible? It works, like it's sensible, it makes sense, plausible. Those are all great ways to say that. And so feasible means all those points make it work. And you could be anywhere in there, but as you'll see when we really get into the guts of this, the points that we're most interested are these purple points. And do you guys remember what Mr. Manlove taught you what those are called in geometry, the corners of a shape? Vertices, very good. So the vertices of your feasible region are going to be the points where significant things occur. They're where what we call optimization occurs. And so if you're looking to optimize, maximize, minimize, whatever, some quantity, it's going to happen at these corner points. And those corner points are brought to you by, well, your ability to graph. So that is that. Any questions about that? No, it's not difficult at all, is it? You can imagine it's nightmarishly difficult for someone whose ducks aren't in a row, someone who doesn't know how to do y equals mx plus b or whatever. So, all right. It is, what time is it? 3:10. Let's do the other example real quick so these guys can get it. And then I want to leave like 15 or 20 minutes at least for example 3. So let's muscle through example 2, because I got to be honest, it's not really all that different from example 1. So just so you know. Are you done?
That was like 3 years, I think.
Okay. Any practice quizzes to turn in?
I didn't get it. No.
Oh, it's a bummer. Um, hate it when it does that. I can't get rid of this. There it goes. Okay. So let me put this one up onto the board. So you guys that just came in late, this is basically what you missed is graphing multiple inequalities on the same grid. More than two specifically. And as typically is the case, you see the boring ones at the bottom. They're the best. They're easy, and they really keep things sensible. So whatever the case may be, whatever X would represent in this problem, you can't do more than 5 of them. Who knows what that means? This is just numbers I made up. All right, let's get to it. So for the first one, same thing. I'm just going to fly really fast through this. We'd get 2y is less than or equal to negative x plus 14. And then we would divide by 2, and we would get y is less than or equal to negative 1 over 2x plus 7. So that should be pretty ho-hum. All right, so this is the new and improved ready to graph version of the first one. Any questions on that? Okay. Second one is going to be, oh, I got a straggler here. Is that a little fella? I would move the y to the other side. So my next line would say 2y is greater than or equal to x plus 1. So that's that trick where you like move it to the right, but then you just read it backwards. Like you guys know how that works. And then we divide by 2 and we get y is greater than or equal to 1/2 of x. Is that supposed to be a 1? I wonder if weird. I wonder how we didn't catch this earlier today. Is this the actual example that I did? I'm gonna have to go back and watch my video that I'm gonna then promptly delete. So is that going to be a fractional y-intercept? Yeah, okay. No big deal, I guess. I did, didn't I? I was doing so well until that. Thank you, sir. Mm. All right, so we got our five constraints. I know some of you I can see are already hard at work with the actual construction of the graph. I really just want to get to example three, but I don't want to go too fast for the sake of these folks that just joined us. So we've got it all ready to go, and now we're going to make the graphs. And so our first one, we're going to start the graph at up 7. So 1, 2, 3, 4, 5, 6, 7, like this. And then the tilt on this one is going to be downhill ratio of 1 to 2. Like such. All right, stick your arrowheads on it. It's just a formality. I get that, but no, it's not a formality. It's annoying, but we still do it anyway. And then the second line, I don't know how this didn't happen to us earlier. I'm a little bothered now well, it's a good thing I'm re-recording because I must have boofed something because I don't remember any fractional y-intercepts. So where are we going to start our graph on this one?
Up 1/2.
Up a half. So mildly annoying, and what sucks about that is if your first point is a tweener, then all of your subsequent points are going to be tweeners. You got to keep staying on a tweener. So we're going to go up 1, right 2, up 1, right 2. Just going to keep doing that. And the line looks like this. So do you know what I mean when I say tweener? I don't mean to be speaking an odd language, but do you see that every time we go up 1 and right 2, we're still stuck halfway between two vertical grid lines, right? So that's why fractional y-intercepts can be a bit pooey. You want to give him a little tap? No, don't throw anything at him. I need you to stay awake, okay? For real. Thanks. Appreciate it. How about the third one? X is less than or equal to 5. What's that all about? Yeah, so let's head over to 5 to the right. 1, 2, 3, 4, 5. Let's draw a vertical wall down through there. So let's take a quick moment and gather our shadings and make sure that everything is going okay. So our shadings at this point would be below this line here. So this shading over here is pretty pointless. And then we're going to be to the left of that little vertical wall, and we're also climbing up from this uphill slope. So you can already see the region taking shape there. All right, our fourth constraint, what's that all about? Um,
That one.
This one is a vertical. Yep. And so we're going to, again, just go to 1 on the x-axis, and we're going to graph a vertical constraint there. So to be greater than or equal to 1 means you have to go to the right of 1 like this. So the region is really, really locked in. And we just have one more little thing to come in. And this one actually winds up serving no purpose, which is interesting that I did this. But like I said, something must have gone wrong earlier. So for y to be greater than or equal to 1, that just means I go to where y equals 1 and I graph a vertical or a horizontal boundary right here. And if I zoom in on that, you can actually see, you probably don't need me to zoom in, but that one winds up really not serving any purpose. Sort of like redundant almost is maybe the word. So the region takes shape, and it's what's the matter? Oh, good Lord. So the region is happening right here within these lines. And so what I'm going to do again is just highlight the region, and it's just good to find the corners first. So there's a corner, there's a corner, and there's a corner, and there's a corner. And then from there, your job is just to shade it in. And what's that called again? The feasible region. Very good. So remember, this region, this bound area contains all of the data points that would satisfy all of the conditions that were laid down. Got to work this much. You can't work more than this. You can't make more than this. You can't blah, 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 blah. When all that comes together, you get this. Are you comfortable so far? Okay, then we're going to do example 3. And for example 3, you need that big awkward piece of graph paper that I gave you. You're going to start seeing more graphs. Sorry for that. I couldn't figure out how to turn it I spent a lot of time, so I had stuff to do, but I really wanted to get a version of this that had a black background. So I apologize. You're gonna get blinded. So you'll notice that this graph, you'll see this also more and more often, that this graph is not labeled. And the reason is I wanted to give you the freedom to label however you wish, not in a happy we kind of creative way, but you'll see very shortly that if we go by ones, you're going to run out of room. You're going to need a much bigger graph. So we have to do one of the most annoying things in all of mathematics in this problem, and that's called scaling. We have to now redo our axes. I'm imagining that you probably do this in science, but I don't know. You know how sometimes, would you not do that, please? Just if you don't want to be a part of this, you don't have to be, but I don't. Just stop. Um, are you done? Like I'm not trying to bore you, but I got stuff to do here, and I can't have you doing that. That's ridiculous. So have you ever done that in science when you have to like change your y-axis to go by tens or by something else? Does that ring in any bells?
Mhm.
Okay, so we have to do that. Because let's talk about the math first. So you need to see the math problem before any of this makes any sense, and then you'll know why I'm talking like I'm talking. So our first one is 30x plus 40y is less than or equal to 3,000. I really wanted to make sure that I snuck into today's lecture a problem that contained numbers that would start to resemble more of the numbers we might see if we were doing some sort of practical application. All right. Before I put the rest on there, I just want to solve this one with you first. And so I want to know what I'm working with. And in order to figure out really what I need to get y by itself so I can reveal the identity of the y-intercept. So someone earlier today said, pull out a GCF. And I was like, whoa, like that was crazy. It caught me off guard. You technically could divide everything, but let's just kind of let it happen as we solve. Okay. Uh, But I thought that was a really cool thing to say. So if we are going to get y by itself, what do we do first?
Let's check.
Yep. So let's leave the 40y here, and then we're going to have our negative 30x on the other side plus 3 grand. And then this is where the whole quote unquote GCF thing sort of just logically, naturally happens. Because what do we have to do now? We divide by 40. And when we divide by 40, naturally, we're going to be reducing by tens here in a minute. So the whole dividing GCFing thing was bound to happen anyways. So let's divide everything by 40. And if we divide everything by 40, then this is where the division magic sort of happens. And so we're going to wind up with something now that's a little bit closer to home. So we're going to get y is less than or equal to
1/3.
negative 3
Oh, yeah.
fourths of x plus what? I think you went a little high there, but try that division again. If you multiplied 40 by 750, you'd actually get 30,000. We don't want that. It's just 75. Good. So you immediately see the need for some more flexible graph paper. Is that rarely do people ask us to graph lines with a y-intercept of 75. We normally, in the normal graph paper that I give you, we run out of room at 10, right? It's just a math teacher thing. We just like to keep it packed in so you can learn the basics. But now it's like, fly, little birdie, 75. And that's pretty small, even in the grand scheme of what we're going to be working with. So here comes a big brainy kind of question. I would accept multiple answers, but there is by far and away a best one. What do you think we should scale that y-intercept axis by?
5.
5 is the best answer in the world that you could give me. The other acceptable kind of answer would be 10. The trouble with a 25 is that then you're cramped. Again, you're kind of defeating the whole purpose of all this freedom you have. If you go by 25s, your y-intercept is going to be cramped way down in the southwest corner. So we kind of want to spread our wings. And a good rule of thumb with graphing is you want to spread out as much as you realistically can. And that's just so that your graph is visible and you can see the things that dorks like me are going to ask you to see. So, and having counted it out earlier, it turns out there are 20 tick marks on each of these axes. I didn't know that until someone told me earlier, but it works out pretty dang good. So if you would be so kind as to scale your axes, and that doesn't mean you have to mark every single one, but you should mark pretty periodically. So you could do like 10 here, 20 here, 30 here, 40 here, so on and so forth. I mean, if you wanted to be real over the top, like OCD about it, you could scale by maybe fours, but I mean, at that point, you're just making it harder than it needs to be. This is good. All right, we can spread out pretty well on this. So to graph this line, let's go ahead and tackle this one, and then we'll go look at the next one. We're going to start at 75. And that is going to be this red dot right here. Graphing can get very nasty now if we make poor choices, and sometimes the choices are sort of inevitable. But in this case, here's my pro tip to you: if you want to keep your life as simple as you can, when possible, scale your axes the same. I'll say that again. If you go by fives on the Y, try to go by fives on the X. It won't always be practical, but if it is, it's not going to hurt anything. And you'll learn that just by experience. If you get on there and you realize, oh, snap, I tried to scale this other axis by 5 and I ran out of room, you live and you learn, and then you go and you rescale it. Can you think of what the benefit is to scaling them the same?
Yeah. The extra stuff in your group.
Yeah, I mean, the math is done for us. So, like, what do you view this? Talk me through, is the guy that taught you algebra, talk me through that yellow slope. What do we do?
Down 3, 8, 4.
It's been ingrained, like it's stuck in your head, down 3, right 4. The trouble with if you scale your axes differently is down 3, right 4 no longer means what you want it to mean. But if the axes stay relatively scaled identically, then down 3, right 4 means exactly what you want it to mean. In this case, specifically down 15 and right 20. So it feels like we're doing exactly what we've always done. We're just doing it with scaled larger numbers. So in order to make the graph of this line, we all are going to just keep going down 3, right 4. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 2, 3, 2, 3. Like that. All right. So at this point in time, we would grab our rulers and make a line that goes through these points. Like such. And I am going to not have my line leave quadrant 1. I'm not even going to put arrowheads on it. Sorry, I'm not trying to set a bad example, but I know what the future holds for this example. So no need to worry about it. And there's actually, I think, one that I might have. Well, let's see how this plays out. Any questions so far? All right, so we've got ourselves the makings of a inequality system, but there's only one on there so far. So here's your next math problem, the next constraint, and the last 3 are softballs, man. They're easy. So this one is negative 10x plus 20y is at least 200. What do we do first?
Add the 10x.
Yes, we do. So we have 20y is at least 10x plus 200. And then finally, divide everything by 20. And if we divide everything by 20, no need to change any signs. And again, that whole dividing, reducing GCF thing just naturally sort of plays itself out. So we're left with y is greater than or equal to, what's our slope? 1/2 of x plus, nice. And again, because we're scaled identically, we can treat this like physically just like we would a regular. I mean, it kind of is. I mean, I don't mean to sound weird, but like understand that on your graph, every tick mark isn't 1, it's 5. But due to the identical nature of the 5s and 5s, it's all good. So we're going to start with our y-intercept at up 10. So that's just up 2 tick marks. And then the slope is going to be up 1, right 2. Yeah. So let's talk shading. Let's go ahead and get a grip on this real quick before we lose sight of it. So the first line that we graphed was a less than. It was before I took it off the board. Shouldn't have probably done that. Anyways, the shading on this line is going to go downhill like this. Okay, the shading on the second line, it's still on the board. You can see it's a greater than, so the shading is going to go up. So we're already locked somewhat into a region. It's not very feasible right now though, because we still include negative values, and that's where the next constraint comes into play. It's not particularly surprising that this would happen. Does anyone want to guess what the next constraint is?
0.
X is greater than or equal to 0. Again, you will see that a lot It merely forces the issue of saying, hey, get your butt up into quadrant one. Okay, we're not going to mess around with negative x values. They're not applicable. They don't make sense in the context of whatever we're doing. So we're going to graph a vertical boundary at 0, like such. And our shading is going to go, of course, to the right, like such. So the feasible region has taken shape, and now we've got just a couple more to lock it in a little bit more specifically, and then we're done. So this next one is x is no more than 40. I don't have my x-axis labeled, and that is not a very good example to set. So I'm going to go ahead and stick some labels on here: 10, 20, 30, 40, 50, 60, 70, 80, 90. Just takes like 10 seconds. So make sure you label stuff. When we don't switch, like if we're just on a normal piece of graph paper and I don't see you switching your scale, it's okay. I'll just assume it's ones. But on anytime we make a switch, we need to tell people what we're up to. All right. So this next one, we're going to go across to 40 on the x-axis. In other words, we're going to go to the right to 40, which is right here, and we're going to graph a vertical boundary. Oops, I forgot to grab my line tool. Might need that. We're going to go up this way. I mean, quite frankly, this part of it isn't even necessary down here. Like I could erase that. And we start to see that we can even erase this part of our constraint, and we can even erase this part of our constraint because we're locking in. And now I can even erase this part of my constraints because I'm locked in even further. It's like the walls are literally closing in. And now we're coming to the smaller side of the 40, leaving us with as many more constraints as some evil person would want to write. I've only got one more for you, and it's this one. That's it. What's that going to be?
Horizontal line.
That's going to be a horizontal boundary. Good. So I'm just going to make a horizontal constraint up here and I made it white, which was really weird. Bad idea. Smooth. And again, I could draw it as long as I want to, but at the end of the day, to stay within the friendly confines, really, this part of it is going to serve no purpose. And this top part winds up serving no purpose. And we wind up with a region that looks like this. And so the reason we want to be pretty uptight about our graphs, and you don't want to be inexact. You don't want to be one of those slobs that graphs 2 points an inch away and then slaps a ruler down. Because as you know, what happens is your line starts to veer off course, and then you can't identify answers to important questions like the ones that I'm about to ask you. I don't think it's difficult, but I'm going to ask you anyways. What are the coordinates of that yellow point?
60, 0.
0, 60. So that is one corner of the feasible region. It's a point that we will study. It's of interest. I am not going to be at all interested in anything that happens along the way. However, I will be interested in what happens when I get to the green point because it's a vertex. What's his coordinate? What are his coordinates?
0.
20, 60. Wonderful. And again, I'm not interested in the things that happen along the way. I mean, normally, like in life, I know they say that the journey is what it's all about, but in math, I'm not interested in the roadway. I'm interested in that. What are his coordinates, that purple point? 40, 45. And then, of course, if we continue to travel, we make our way down to this southeast corner. What are his coordinates? 40, 30. And then finally, we make our way, and I'm out of colors, so I guess I'll return to purple a second time. So, because I don't want to, I could do white, but that would not show up. So, big purple guy down there, what are his coordinates? Good. Listen, that's really the groundwork that I need to lay. I don't honestly know. I'm almost done and then I'll shut up. I don't honestly know if we're going to start the word problems on Monday, just because today's lesson, I knew after first hour that this was the case. It took longer. I'm a fool sometimes. And why do I think I could do this in 20 minutes? So Monday might wind up being a mechanical work day on just plotting feasible regions with no purpose. And then Tuesday, we would start the word problems. If I sneak attack you and we just jump right into the word problems, don't be like upset or anything like that. But I wonder if a day to just do this might be good. So I'll think about it over the next few days. Do you guys have any questions for me? All right, you feel like you can handle all this? The harder ones will always be the ones with the big numbers, because then that's when you got to start dorking around with your axes and changing your scales. And sometimes you got to scale by 20 or 100 or 50, and it gets a little hard. So